Hello everyone, my name is Jungwon Kim at Korea University. It's my great pleasure to have a chance to make a presentation at iCoin. Today, we're going to talk about advanced deep learning method for autonomous mobility. So this presentation is organized as follows. First of all, I would like to introduce a brief outline of this lecture, and then I would like to introduce several applications for deep learning applications to autonomous mobility platforms. So first of all, introduction. So in current ages, we have a lot of advanced technologies for autonomous mobility. So autonomic vehicles are moving around without any kinds of control. They are moving around with the autonomous intelligence. For that purpose and applications, we need advanced techniques. So first of all, it should be deep learning based intelligent computing. It means that based on the deep reinforcement learning algorithms, they should be controlled in a sequential manner to achieve the main goal of the autonomous mobility applications. So here we want to design an algorithm for dynamic trajectory control and optimization for autonomous mobility vehicles. In addition to that, the algorithm should be stabilized. It means that the network is not well coordinated with autonomous mobility platforms. In autonomous mobility platforms, the vehicles are moving in and out without any expectation or predetermined rules. That's why we have some autonomous coordination and cooperation. For that purpose, the data flow might not be stabilized because we cannot estimate any kinds of the incoming or outgoing flows. Be, be, without these kinds of the centralized control, even in that case, we need to maintain the stabilized computation. So here we have to say that traffic and queue-aware stabilized computing for learning-based autonomous vehicles are required. Lastly, truthful computing. So the vehicles are moving in and out without any centralized computation. That's why we may not trust the incoming vehicles. So in order to take care of these situations, we need on-demand and ad hoc access from unauthorized autonomous mobile vehicles. In order to take care of these cases, we need truthful computing. So in this tutorial, I would like to introduce these three major research topics. So here, let me introduce one by one. First of all, I would like to introduce deep reinforcement learning for autonomous mobility platforms. So we're gonna talk about the first one. So before starting, we may want to have some brief introduction to reinforcement learning. So reinforcement learning history is quite long. So in 1954, Professor Marvin Minsky's PhD dissertation has the term of reinforcement. So in his PhD thesis, the title was Stochastic Neural Analog Reinforcement Computer. From this time, we start to use the term of reinforcement learning. So fundamentally, this algorithm is the analogies with the animal learning and psychology. And one of the most successful applications is job shop scheduling for NASA space mission in 1997. So when I was an undergraduate student, I saw several robot soccer players in my university. So it was 1999 or something like that. So most of the algorithms are designed on top of the dynamic programming or reinforcement learning. That's why robot soccer is one of the famous reinforcement learning applications. So when we can use reinforcement learning, when reinforcement learning can be used, the algorithm can be used when we want to find optimal action sequences. That means that in general, conventional deep learning algorithms, we want to find the optimal solution in a given problem at one time. For example, we want to do the classification, then we can get the answer and that's it. That is one-time solution. But the reinforcement learning is designed for sequential decision making. It means that one-time solution is not enough. We want to maximize the reward that can be the benefit which we can take by taking any kinds of actions, but we have to make an action sequentially. So this is not for single optimal solution. This is for action sequences. Okay. So in order to take an action, we need to define the actions and their corresponding rewards. So these are all we need to do, or we need to require. So based on this basic information, we can start the reinforcement learning computation. So this is one example about that. In industry or smart factory, we have some robot. The robots are designed for main purposes. So in general, when you think about the robotics, we may think about the humanoid. But here, our basic assumption is that the robot is designed only one single purpose. So this is purpose-driven robot that is also called industrial robots because they are usually used in the manufacturing or factory site. So in the left-hand side, the robot arm is doing some cooking. So then we need to define the trajectory of the arm in order to make delicious food. In the right-hand side, we have another robot arms, and they want to do some manipulation or they want to do some manufacturing. So suppose that we are in a vehicle manufacturing site, and then the robot arm wants to paint the given vehicle. So in that case, the robot arm start to paint the vehicle body, but we want to do it as soon as possible, but we do not want to multiple painting in order to avoid any kinds of cost inefficiency, or we want to cover entire space for better condition or for better result. So that is based on the reinforcement learning, because this is just not for the single action taking. They have some trajectory of the arms. That's why these algorithms are fundamentally designed by the reinforcement learning. So here the action setting in the given state is called policy. So policy is for the mapping between the state and action. So the given state, if we can define the action about that, then we are saying that we have some policy about the reinforcement learning. So in theoretically, reinforcement learning setting can be explained as follows. The general reinforcement learning problem is formulated as a discrete time stochastic control process. We said that discrete time because we are doing some discrete time control over the given condition. And then this is stochastic process because our action taking is fundamentally based on the probabilistic decision making. Also, we are doing some action taking that can be called control, and this action taking is not only for a single decision. That's why we have process. That's why, as you can see in this slide, reinforcement learning can be mathematically called as a discrete time stochastic control process. So as you can see in this illustration below, we have agent. Agent is located in environment or state. In a given state, then the agent has certain amount of the actions. So individual actions has its corresponding reward. So we will gonna take the action which can take the maximum reward, and then they can make an impact to the environment. That's why we can move to another state, and the given updated state we can take another action and so forth. That's why we are saying that the reinforcement learning procedure is a sequential decision making. So here we can think about the gameplay as well. So in a StarCraft game or something like that, we have some expert data, and based on the expert data, as the game goes by, the player will make different actions based on the given statement. So if the agents are designed based on the reinforcement learning, the agent can make an action based on the given condition or state. As the states are updating as time goes by, the action can be varied as well. That's why our reinforcement learning algorithm wants to make an action like a human being. So that is in order to win the game. So that is a fundamental application in reinforcement learning or deep reinforcement learning. So in that case, we in in this case, in a given state, minimap and screen, as you can see, in the left-hand side in blue characters, we have given minimap and screen, and the given condition, we are taking an action to select some unit and to send the unit to the other direction. Then we are taking some drag actions. So based on the data, so we can make a train for the agent, and then if we have a new state, then they can take on approximated appropriate actions. So that is fundamental goal of the reinforcement learning. So this action is not a single action. So in a given, by taking an action, our state will be updated. In the updated state, we can take another action and so forth. That's why this kinds of training is required, and this kinds of sequence is also called reinforcement learning. But in this case, we just talked about the single agent. But suppose that we are dealing with multiple agents. As you can see in the left-hand side, we have two agents in parallel. So in the first agent, you have agent 1, and then we have agent 2. Agent 1 has action sequences A sub 1, B sub 1, C sub 1, and D sub 1. And agent 2 also has some sequences, state sequences, A sub 2, B sub 2, C sub 2, and D sub 2. And these action sequences are trained in a single neural network. By considering the single neural network, the information of individual agents can be mixed together in hidden layer computation. That's why we can, even though we can take on action for individual agent, the action computation was fundamentally under the consideration of the other actions or state information. That means that their informations are shared. So even though the two agents are separated, their informations are mixed in DQN, a single neural network. That's why they can be cooperated and coordinated because they share their own information over there. So in this case, in general, we are saying that this architecture is a CTDE, which means that centralized training and distributed execution, because we are doing the training in a single neural network here. That's why this is for the centralized training. So let me see more details about this architecture. So here, as I told you before, even though individual agents' informations are coming to here and they are not talking to each other, but in this single neural network, their informations are mixed. As you can see below, this is one hidden layer, this is next hidden layer. If we move step by step, and then this agent information will go to the next one, but this information is going to the next one, as well as the other information will take the mean, and then the information is applied to here. That's why by taking this action further and further, we can mix the information all together. Okay, then we are saying that we can get some hint for the coordination and cooperation. So in this case, this is for the training procedure. So during the training, they are doing some training in a centralized manner. Once they are done for the training, this DQN is distributed to individual agent, and then individual agent can work based on the given neural network. That's why the execution is distributed. So we are saying that this is centralized training and distributed execution. So let me see more details or mathematical backgrounds about that. So as I told you before, agent 1 and 2's informations are coming to the neural network, and these values are encoded to numerical values, because the state information may not be in numerical data. That's why the data should be translated to numerical values. That is called encoding here. And then we have two steps here. The first one is communication variable definition. The next one is activation function calculation. Okay, so suppose that I'm the agent 1. I'm the agent 1, and my value is here, but we want to define the communication variable, which means that if I'm 1 and there are the other agent 2, 3, and 4, then we are taking the average of the 2, 3, 4. That's why total number is 3, because we are all in 4. That's why we have j minus 1, because j means the number of all given agent. But here we have 4 agents. However, we are taking the average for the other 3. That's why we have j minus 1. And then we are taking the summation for the others, and then we take the average about that. the collection of these kinds of the values is called communication variable. Okay. And then we have activation function, which means that I'm h sub 1 and comma 1 super 1, and I have my own communication variable, this where this is organized by the other agent information. And then this value and this value will be in the activation function, and then we can define our next step value. So next step value contains the information of the other agent. That's why we can do cooperation and coordination based on this numerical computation. So that can be. So I already talked about the communication variable definition, right? So if I'm one, I will take the average of the others. That's why we have this one, okay? And then we can make a communication variable by taking the average of the others. And then we are taking my own information and communication variable, and then we take the activation function over there, and then the value is stored in H here. That's why this will be the hidden value for the next step. Okay. So let me introduce this one again in one illustration. So suppose that we have 4 agents in the network. This is number 1 agent, number 2 agent, number 3 agent, number 4 agent. Okay. And then we calculate the communication variable. So if I'm 1, I'm calculating my own communication variable with the other information. So we have 3. That's why, entire number of n, without myself, we have n minus 1. That's why after adding all the information here, and it will divide by n minus 1, and then we can calculate the communication variable. So this communication variable is only for this first hidden variable. That's why for the second one, we will calculate the communication variable with the information of 1, 3, and 4. If you want to calculate the communication variable for the third one, then you can take the values of 1 to 4. Lastly, if you want to calculate the communication variable of h sub 4, then you can take the average of 1 to 3. So you can see that you can calculate communication variable in that direction. And then the hidden variable and communication variable values will be added into the activation function, and it will gonna be the next steps on agent one's information. Now, by doing some calculation for a single hidden layer, then the values are all mixed together, and then we can compute the next hidden layer. And then we can go further and further with 5 or 6 hidden layers. Then the information in individual agents will be mixed all together properly. So then we can say that their informations are mixed all together. Okay. So in this case, so these kinds of the multi-agent reinforcement learning algorithm called ComNet. Okay, so in ComNet, so these all agents are identical. That's why we can do that kinds of the all mixing computation. So if we want to define somewhat much more complicated architecture, which can define the relationship among the given agent and the strongness of the relationship or the given graph, and then we can define another algorithm. So that is called G2A net. So in G2A net, we are not assuming that the agents are all identical or homogeneous. In this G2A net, we assume that these agents are heterogeneous. That's why, as you can see here, agent 1 can make an impact to agent 2. Okay, agent 2 can make impact to agent 3, but agent 3 cannot make impact to agent 2. And then as you can see here, 2 and 4 has no relationship at all. So these kinds of sophisticated relationship can be defined by this graph. In addition to that, even though the edges are existing, the values are not same to each other, which means that the strongness of the relationship can be separately defined in G2A net. So how we can work with G2A net. So suppose that we have 4 agents here, and then first of all, we have to define the graph for the relationship, okay? And then once we are defining the edges here, then we have to define the strongness of the edges. So that means that we have to define the weight on top of the edges. So we have 2 steps. For the first step, in order to make a graph for the relationship, we have to make a connection at first. On top of the connection, we have to define the weight. So that's the procedure what we have to take. For the first step, that can be done by hard attention. For the second step, it can be done by soft attention, okay? So as we can see here, multiple agents are existing, and the relationship of the agents can be defined as a graph. This is the example about that. So how can we do that? So this is a brief architecture about G2ANet. So suppose that we have one state and they can be encoded, and then they can pass by hard attention or soft attention, both of them. And then hard attention will define the graph, soft attention will define the weight, and then finally the information can be combined. Then we can define the graph as well as their corresponding edge cost. And then we can decode the data and we can finally get the answer about that. Okay. So this is also reinforcement learning because we put the state in the neural network and we define or we calculate the actions about that. So in a single neural network, we put the state and we can get the action. Okay. So this G2ANet architecture also reinforcement learning in brief. So as I told you before, we have to define so this one, if we have some statement here, by passing dense and RNN, we can make some encoding about that. So this is the encoded data by doing this encoding. So by doing the encoding, the older state information can be converted to numerical values. The encoding result will be come to a hard attention. That's why based on this one, you can make adjacent matrix which can define the relationship about that. So in this case, in 1, 2, we have 1. That's why 1 and 2 has connection. And as you can see here, 1, 3, there is no relationship. That's why there is no edge from 1 to 3. So based on this adjacent matrix, we can define the graph at first. Based on that, you define the soft attention. That's why you can calculate the weight about that. So by doing the element wise operation here, and then you can put the weight value on top of the edge. Those are existing. Okay. Then we can make a graph as well as we can define the weight. So based on this one, then we can find the relationship of the agent, and then we can start the multi-agent reinforcement learning calculation. So this one is one example about that. This work was published by IEEE Transactions on Vehicular Technology last year. So here the mobile UAVs are flying, and then they should be charged by the EMS system, energy management system. They are charging the UAVs in wireless power transfer, and then we have to schedule at first, and then we have to determine how the energy should be allocated from this EMS to this individual UAV. For that purpose, if the energy is not sufficient in a single EMS component, then we should be purchase the energy from outside utility company, which takes some cost. That's why in order to minimize the cost expenditure, we want to accelerate the energy sharing among ESS. That's why we made a reinforcement learning algorithm based on that in this given multiple agent. That's why in addition to that, in this system, we can easily assume that EMS are identical. That's why we do not need to G2ANet here. We just use the ComNet in order to implement this architecture. So this is the ComNet architecture we used. So in this illustration, we assume that we have 4 charging towers, and that's why we have 4 state and 4 actions. Okay. So states means the current energy amounts. Action means how much energy should be distributed nearby. Okay, and we have in a neural network for the centralized training, we have 6 layers here, and then we have these kinds of the information mixing when we compute the hidden layer inside the here in order to realize cooperation and correlation. Okay. In addition to that, the agents are drones here. So in this case, we want to design autonomous surveillance, coordination, and control. This is recently published, accepted by Transaction Zone Industrial Informatics this year. And then you have UAVs are here, and then they are flying here, right? But if we are designing this algorithm with a single agent, they have same reward functions. That's why they will work all together. They move all together in the same direction. But that is not the case where we want. We just want let them distribute further and further, and then we can extend the surveillance area. That's why in order to realize that applications, we have to use the multi-agent algorithm. Okay. So here we can easily assume that all the given agents are identical. That's why we do not need to use G2ANet here. We just use ComNet here. Okay, that's why we have this architecture. Furthermore, we can consider the drone taxi coordination and control. So multiple drone taxis, here the 4 are existing and they are flying in this given network. If we are using single agent, then they will work similarly. That's why they are moving in a similar directions. Then we cannot serve this amount of people in the network. But as you can see left hand side, if they are designed as a multi-agent system, then they can fly and then they can be distributed workers, and then we can make a service for more and more users. Those are distributed in the given network. Okay, this work was published in last year in one journal. Next one, for the stabilized computation, I would like to introduce Lyapunov optimization briefly. So second one, for autonomous mobility, we have to consider the stabilized computing. So I would like to introduce this one very briefly. So if you are doing some network research, you always do the optimization or convex optimization, and we want to solve our problem for utility maximization, the scheduling performance or something like that. Then we are using a linear programming or convex programming, but in these formulations we have no specific consideration on time. But what if our optimal solution introduces delays? So we thought that the action A is our optimal, then you can choose the action A multiple way. But in that case, if the A action takes a lot of time, then it will gonna make a delay in the system. It will be harmful. That's why we need to think about the time as well. So if our solution, optimal solution introduces delays, then it will be harmful for real-time mobile systems. That's why we need to think about the trade-off between utility and delay. So for that purpose, we have to do the time modeling at first, based on the queue, and then we have to stabilize the queue. That's why we have to define the queue as Lyapunov drift at first, and then we have to make it stabilization. Then we can do time average optimization eventually. So as I told you before, in utility and delay, if there exists a trade-off, then we can use Lyapunov optimization. The delay can be modeled as a queue here, and our utility can be energy. We may want to design energy efficient system. We may want to design high quality video streaming. We may want to design high PSNR system. We may want to design high accuracy learning system. So these kinds of criteria can be good examples for utilities. So this is one simple example about that. Suppose that you have your own smartphone and you want to control this smartphone. So suppose that within here you have a processor, it has multiple cores inside. If you allocate more and more core, then it's not good in terms of the energy management. However, you're gonna process a lot. Then if you touch this screen many times, it's gonna make a lot of tasks, but it can be processed faster. That's why it's good for stability, right? So that's why you can observe the trade-off between the energy consumption and stability. That's why you can use the Lyapunov optimization here. So it can be formulated as follows, but let me just briefly introduce the below at first. But briefly, when you look at the left one, this is your time average utility. Okay, and then this can be minimized, but your basic constraint is that the queue should be stabilized in order to avoid delays. Then this can be approximated to follows with a constant gap approximation. So this y sub 0 becomes objective functions here, and alpha of t becomes your action, q is your queuing backlog, a is your arrival process in the queue, b is your departure process in the queue. So the single equation can be derived by the use of the Lyapunov drift in order to model the queue stability. So here, this is our objective. This is our stability condition. So let me give you some example about this one. So first of all, if the system has large delays, then Q might be infinity. Then in that case, this is infinity. That's why left-hand side can be ignored because this is too small comparing to the right-hand side. In that case, you have to minimize this one. Then A, if you can control the arrival, then A should be minimized. If B can be controllable, then minus minimization. That's why it can be maximized. It means that if the queue is almost full, then you have to control the arrival. You should minimize the arrival in order to avoid the overflow, or you have to accelerate the processing. That's why you have to minimize the A, but you have to maximize the B, which is the same with this numerical result. So on the other hand, suppose that there is nothing in the queue is 0, then this one becomes entirely 0. Then you want to focus on your optimization criteria. You can focus on your objective function, then you just minimize this one. You can take the action just like that. Okay, so based on this equation, you can control the system in a stabilized manner while optimizing your utility. So here you can see the result, you can see the example about that. Co-allocation. Suppose that you have a lot of tasks in the queue, then in a processor in a smartphone, then in order to avoid the overflow, even though it takes a lot of energy, you can put a lot of cores in order to accelerate the departure process. If the queue is almost empty, then you don't need to do that. In order to save your energy, you can save the number of cores here. So then you can control the number of cores in departure process with Lyapunov optimization under the observation of this trade-off. Okay. So let me give you one more example about that. This project was done with Yonsei University from 2018 to 2021. You have drones there, and then we have a mobile edge computing device, and drone can capture one image, but drone has very limited energy. That's why sending this large amount of data to the MEC directly is not possible. That's why they are doing the compression at first, and the compressed data will be delivered to the mobile edge computing for, okay, then we can minimize the size of the delivery data. Once they get this data, then they may not satisfy with the quality of this data because they are compressed. That's why we want to improve the performance of this one. Then we use compression artifact removal network in order to enhance the quality of this image. Okay, so in summary, in original image, in order to transmit this one as fast as possible, they compress at first and then they deliver, and then once they got this one, they recover with the deep learning architecture, and then we can get the original one. This is kind of the virtualized bandwidth extension. Okay, but in this case, the arrivals are random. Then this can be overflowed or this can be empty. That's why we have to define the queue here, and then we have to control the compression ratio, the recovery ratio. So if we have more deeper and deeper network, it takes a lot of time, but the performance will be good. If the network is very shallow, then in that case, the performance is not good, but it's very fast. That's why you can observe the trade-off between the accuracy and delay. So you can control that feature with Lyapunov optimization. So as I said before, we may have several neural network. As you can see here, if the neural network has a small number of depths, then the quality is not good. It's just 30 dB but if you have deeper network, it's 33 dB. So this is much better in terms of the quality. However, deeper model takes more time. In this case, we have shallow model. The time takes very little, but as you can see here, it takes a lot of time. That's why you can see that the trade-off, there exists trade-off between the quality and the processing time, the delay. Okay. So as you can see in human vision, so left-hand side, this illustration performance is not that good, but this recovery performance is very good when you look at in the larger images. That's why you can see the difference between them. So you may have multiple neural network at first, and you can select one. And then if you have a lot of queuing delays, then you select this one because because you need faster processing while sacrificing certain amount of accuracy. But if you do not have any kinds of delay there, then you don't need to worry about the delay. That's why you can have enough time. That's why you can choose the maximum performance neural network architecture, the last one. That's why depending on the queuing delay, you can select one in a given set. So this is required technique for system design for machine learning or deep learning. So also you can control the number of hidden layer inside there. Okay. So then if you can control the number of hidden layers, if the time is not enough, then you can take the image in the middle of the process. And then if you have enough time, then you can take the image in the last stage. So you can design these kinds of neural network architecture, and then you can put the cost function in the middle of the hidden layers, then you can make this one. Okay. So this is called depth controllable neural network architecture, which was proposed in IJCNN 2019 by my lab, the other students. So then we can think about this abstract system. So this is stabilized computer vision platform. So suppose that you have CCTV here, and then the CCTV is doing some sampling over here. And then CCTV images are coming here. And then if we are doing some detection here, and then it takes a lot of time sometimes, or it takes more time. So depending on the queue size, you can take the neural network architecture, which is low complexity but faster, or you can select another neural network that has high accuracy, however is very slow. You can select one neural network architecture depending on the queue size. If the queue size is very long, then the accuracy is not important at all. You just satisfy the queue stabilization, queue stability. That's why you may choose this one for faster computation. If the queue is almost empty, then you don't need to worry about the stability anymore. That's why you will pursue your main objective, that is the high accuracy. That's why you can select one depending on the queue bank size. So that kinds of algorithm can be defined as follows based on our previous equation. Okay. Then you can see here when we are doing the Lyapunov-based dynamic control, and then you can see that in a certain point they can be stabilized, and then this is the selection of the model. Then as you can see in the black curve, they are moving around, which means that they are changing the neural network architecture in the middle of the process. Or previously we control the departure process because we control the neural network architecture. But in this system, revisited system, the departure is fixed, but then we have to control the arrivals of this queue. So the CCTV camera can control its own sampling rate. If the processing here is quite slow, then in the case you will gonna have more and more queuing backlog, then in that case it can slow down its performance sampling. But if a queue is empty, then in order to increase the security accuracy, then it can increase the sampling rate. That's why the sampling rate can be controlled depending on this queue backlog size based on the Lyapunov optimization framework. So we made an algorithm about that here. Okay. So as you can see here, the black one means the faces per frame. So in this case, when you look at this one, in this frame, we have 7 people. So if we are here, we have 5 people. Then when you look at this red curve, if you have more and more faces in an image, then it takes more time for processing. If we have a smaller number of faces in an image, then the time takes more. It means that the departure process in our previous system is random. So departure is random. That's why the Q backlog can be varied, but we cannot do the estimation. So in that case, based on the Q backlog size in a given time, we can make a control for by selecting the sampling rate. That is our proposed algorithm in this work. So here again, we saw that our previous proposed algorithm is stabilized. It works in this stage. That's why it is not diverse. Okay. So based on if you can observe the trade-off between the delay and utility, then you can make a simple Lyapunov based algorithm which is very scalable, distributed, and low complexity. So based on that theory, our lab made these kinds of publications. If you have any interest on this Lyapunov control for learning system, then I highly recommend you to read these papers. Next one, trust computing, right? For the trust computing, I would like to introduce the truthful resource allocation for autonomous mobility. So this is the last part. So in this last part, we want to design an algorithm for truthful computing in autonomous mobility, and the algorithm is fundamentally designed by economic algorithm that is called auction. So for distributed resource allocation, we generally use economic theory. For example, game theory, auction theory, stable marriage, something like that. So in this slide, in this lecture, I would like to introduce auction-based resource allocation. Okay, because auction-based resource allocation is generally called truthful if we are considering second price auction. So from now on, let me introduce what's the auction. That is one of the famous economics and distributed optimization techniques. In general, when we think about the auction, we think about first price auction, FPA. So we have one selling item. This is the resource in the network, and the seller tries to sell this one. And then the seller can be also called auctioneer, and the revenue can be defined. So in this case, there are three bidders here, and then A's bid value is 10, B's bid value is 8, C's bid value is 6. Then in that case, A's value is the highest one. That's why A will be the winner. So A will get this picture, and then A will pay $10 to this auctioneer. Then we are saying that the revenue, the benefit in auctioneer is $10 because this guy A paid $10 to this auctioneer. But in that case, if you are B and if you really want to buy this one, then it can pay a little bit more than 10 because it can be the B can be winner. Suppose that B tries 10.1, then B will be the winner because it has a little bit more than the A. So here we are saying that the bidders should be strategic, which means that they should look at the others all the time and they have to pay a little bit more than the competitors, okay? So here we can define the concept of the utility as well. So in utility, in A, utility can be calculated as follows. The bid value minus payment. So here the bid values are 10, 8, 6. So utility of A, utility of B, utility C will be 10, 8, 6, but you have a minus payment. B and C has no payment because they did not pay anything. But A has payment as much as $10. That's why they pay 10 here, and then the utility becomes 0. So utility can be the budget, remaining budget. So if he has 10, he paid 10, then he has nothing. Then utility becomes 0. B still has $8. That's why this becomes 8. C still has $6. That's why utility C is still 6. So this amount means the money at least they have. But now let's look at the second price auction, right? Second price auction works as follows. The bid value is 10, 8, 6, similar to previous one. And then in this case, A becomes winner because A's bid value is the maximum. That's why A becomes winner. However, the payment will be the second one, the $8. So A becomes winner and A will pay only $8, not $10. then the seller will earn $8, right? So when you calculate the utility, the bid values will be 10, 8, 6, as you can see here, but only A paid. That's why A has negative values here. And then A paid $8. That's why minus 8. So the utility becomes 2. That means that A may have at least $10, but pay $8. That's why A may have at least $2. So as I told you before, these amounts are the amounts where individual bidders at least has. Okay, but second price auction, why we then have to use the second price auction? Because in general we believe that second price auction is truthful, so we need truthful computing. That's why we want to use the auction here. So in order to show that second price auction is truthful, let me give you one more example here. Suppose that A is bidder, the bid value is $10, but B only has $8, but it make a fake bid, $100. So this is malicious user. This user wants to take this one anyway, and then they make a fake bid just like that. And A bid value is 6 here. Okay, then when you look at this one, the bid values are 10, 106. That's why B will be the winner for sure. And then the payment will be the second price. Here the prices are 10, 106. That's why second highest one is 10. That's why B should pay 10. And when you look at this one, 8, B only has 8. That's why B cannot pay 10 here. That's why the utility of B will be bid value minus payment. The actual bid value was 8, but he has to pay 10. But then he has no money. That's why when the utility becomes negative value, it means that B has no money to pay. That's why the malicious user has no benefit to make a fake bid. So individual user in this system does not need to make a fake bid, because even though they make a fake bid, they win, but they have no money to pay. That's why individual users in the system should be very truthful. That's why for truthful resource allocation, we consider the second price auction. Okay. But the only problem is that auctioneer cannot get the maximum one. 10, 8, 6. In that case, A will be the winner, but only paid 8. That's why seller may be able to get $10, but in second price auction, they get only $8. That's why the revenue is not maximum. That's the main problem in the second price auction. So let me summarize about that. So in summary, when we look at this one, we are saying that we want to use the second price auction because it's truthful. So in autonomous mobility system, maybe autonomous vehicles are coming in and out around or working around. If they join the network, they need some resource allocation. For the resource allocation, if they are using second price auction, then we can guarantee that the computation is truthful. That's why truthful computation can be guaranteed in second price auction. However, the auctioneer, the guy who is selling the resource, auctioneer's benefit, the revenue is not maximum. Okay, so revenue is not optimal. That's the problem in second price auction. But in first price auction, if A's bid is $10, then if A is winner, then the seller get the 10, the maximum one. That's why this is revenue optimal. However, this is not truthful. So we want to take the benefit of these ones. That's why we want to design the optimal auction. So optimal auction means that we want to design an auction that is truthful as well as revenue optimal. Okay. So that technique is called virtual valuation. So this is the fundamentally based on the Mearson auction. So suppose that there are two bidders here and they have their own virtual function. That's pi sub 1, pi sub 2. So their bid values are just like that. This is the bid value of the first bidder. This is bid value of the second bidder. But then they are doing some bidding. They are not doing the bidding based on this original value. They will put this value into this function at first, and then the b sub 1 becomes this value, b sub 2 becomes this value. Because this function is pi sub 2, the second bidder's its own function, and then b sub 1 will be applied to the function of the first bidder. That's why this is the converted virtual bid value for the first user, and this is the virtual bid value of the second bidder. Okay. Then we compare here. We compare here. Then we will take the maximum one. That's why number one becomes winner because number one's value is higher. And then we have to, then number one's payment should be determined based on this value. But this value is virtualized one because this is the result of the virtual function. That's why we want to convert this one into the actual value again. But in here, the one is winner. The one has one knows only its own function. That's why the invert function will be applied based on the q sub 1 because the user one knows its own function only. It does not know this one at all. That's why for the inversion computation, you're gonna take the inversion of the pi sub 1. That's why in order to calculate the payment, we will take the virtual value of the second user, and then we will take the inversion function of the first user. That's why in that case, we have to get this value. So here, this one was winner. This one was a second price. So even though number one becomes winner, it has to pay this amount. Then we have this amount gap between 1 and 2. However, by using the virtual valuation, we can increase this amount of the revenue. That's why the number one will pay Q sub 1. That's why in terms of the seller or auctioneer, the revenue is almost nearby. That's why by using virtual valuation, the agent can, the auctioneer can increase the revenue as much as this amount. Okay. So that can be computed by this neural network. That's why the auction, nowadays there are a lot of research that is computing auction with deep learning framework, neural network. So as I told you before, this is our payment. For the payment calculation, we have B1 and Bn, n bidders. And first of all, we pass the ReLU because we want to eliminate negative values in statistics. And then we are doing the sampling, and then we are putting the values in here, and then again we take the inversion function. Then these kinds of the neural network computation is very similar to these kinds of the virtual valuation. That's why nowadays we are using auction with deep learning. Then we can get the truthful result as well as we can get better revenue. That's why it is good for everything, right? So this is the performance evaluation result. For the first result, bid values are just like that. We will gonna eliminate negative values, and then there are two fourths and fifths values are just like that. So then as you can see here, left one is 0.44, right one is 0.737. That's why left one is bigger. That's why this one will be the winner. Okay. However, if you are doing pure second price auction, then you will take the second price value. That's why this will be chosen. But when you are doing deep learning computation, then you will get you will increase this value. Okay, this value will be increased to this one. Then you have almost similar payment. That's why revenue is near optimum. Okay. For the second round, the first one is negative values. That's why we can eliminate this one. You have 1, 2, 3, and 5th. Among these given 4, this is the first price. This is the second price. So this one becomes winner, and then this winner will pay the second price, this one. However, by using deep learning, this payment value becomes 0.95, almost similar to the winner value. That's why this is near revenue optimal. That's why in this case we are using second price auction, and revenue is also increased. That's why this is the better solution comparing to the others. So these kinds of system can be used in many applications. So when this one was firstly introduced by Harvard University economics, so many network researchers or network economics researchers start to use this auction with deep learning framework. And one of the first work was by Professor Niato at Nanyang Technological University, and this paper was published in ICC 2018, and as far as I remember, this was revised and published in Transactions of Mobile Computing last year. So here, mobile devices are existing. If they want to do some blockchain mining, they have to borrow some resources from this cloud. That's why they have some contract about that. But by let this one is doing some computation here, they have to pay something. But but the resources here is limited. That's why they should do the auction in order to get the resource from the cloud. That's why they are doing some competition based on the bidding, but the benefit here should be maximized. That's why we are using second price auction for the truthfulness. In addition to that, we use the deep learning to improve the revenue in this auctioneer or seller. Okay. And next one is multi-UAV charging scheduling. So suppose that there are multiple drones in the sky, and then we have one charging panels here. And then if one malicious user is located here and taking the energy from here forever and ever, then the other drones will be dropped down. So that is not good in terms of the reliable or truthful computation in autonomous mobility. That's why we designed truthful mobile charging schemes in our previous paper, Transactions of Vehicular Technology 2019. So this one is joint work with UC Irvine, Marco Rebrato professor, who is another tutorial presenter in iCoin here. And then here, multiple drones are existing. They are bidding. They are doing the bidding for getting this charging resource. And then we want to increase the benefit in this charging providers as well. So that's why we designed the algorithm with the second price auction, and then we use the deep learning in order to improve the benefit in this auctioneer. Okay, so as you can see in the plotting in the revenue, so this is pure second price auction, and then the statistical distribution of the revenue is from here to here, and this is median. Okay, but when we are using the deep learning architecture in order to improve the revenue, then you can see that they have improved the revenues here. We have k equal 1 as well. So in this case, the sensitivity of the deep learning mechanism is not that good here. This is very sensitive because k means the sensitivity values. Okay. So as you can see right hand side, when you are using second price auction, the revenue is still very flat because they have uh, no randomized training procedure or iterations or something like that. They just introduce the static value just like that. But if you have more and more higher k values, then your deep learning framework is very sensitive. That's why, as you can see here, higher k value shows the better revenue. You can see that there are big differences or big improvements if you are using deep learning architecture on top of the auction-based resource allocation. So here you also can see that our revenue is much better comparing to second price auction, pure second price auction. So this gap means the performance improvement by deep learning. Okay, and then we did another simulation with more and more drones and so forth. But in any cases, our proposed algorithm is much better in terms of the revenue optimality in auctioneers. So this is the last page of our tutorial today. So in order to design autonomous system, we need a lot of algorithms, but we want to design an algorithm which should be stabilized for autonomous unexpected situation, or the algorithm should be very truthful because unexpected device will join our network or leave. So in that case, we have to trust them. That's why truthful algorithm is also required. Lastly, intelligent computing is also required in order to define the optimal trajectory. But in that case, as we discussed before, we use the multi-agent deep reinforcement learning because multiple devices are located in the network. They should be cooperated and coordinated in an intelligent manner. That's why multi-agent deep reinforcement learning based algorithms are required. So here in autonomous mobility research, I would like to highly emphasize that we have to design multi-agent deep reinforcement learning based intelligent algorithm. We have to design stabilized algorithm for avoiding any kinds of overflow or unexpected situation. Lastly, our proposed algorithm should be truthful in order to trust the devices who are joining and leaving this network in an ad hoc manner. Okay. So this is end of the presentation today. It is my honor to have a chance to make a presentation here. If you have any questions, please leave your message in this email address. Thank you very much, and I hope you enjoy this conference. Thank you.